Welcome, dear students, in this new chapter of liquid drop model. In this chapter, what we are going to do is we are going to develop a nuclear model, which is called liquid drop model. There are many models. We have developed atomic models so far till your SYBC. You're familiar with Bohr atomic model, vector model, Sommerfeld model. The objective of all this model is if it can give a theoretical explanation to the various atomic phenomena which occur. Similarly, the objective of this nuclear model is this model able to correctly predict the nuclear phenomena? You ask me what is nuclear phenomena? Is radioactivity, fission problem, and there are a whole lot of problems which we will be dealing with very extensively in this chapter. It's a big chapter, and we will be evaluating at the end the merits and demerits of this model, which are the problems which it is able to answer correctly or to fairly good accuracy, and which are the problems which it is not succeeding to answer. So, this is going to be the objective of this chapter. Why it is called a liquid drop model, all those things we will take it up in the future lectures. Today, what we're going to be discussing is some of the general characteristics of the nucleus which is observed in nature. One of such plot is called a Segre plot. Segre plot plots n, that is number of neutrons, against z, that is number of protons, for all atoms which is existing on this earth. It is a graph which plots between two variables, one is neutron, another is proton. This line out here, now let me explain this graph. This line, can you see this straight line here? This straight line means n is equal to z. But as you can see, up to this point, okay, this dark line, this line, zigzag dark line, can you see this line? This is actually a stability curve. Stability curve. Okay. Now if I have to plot it, the stability curve looks like this. This is your n. This is your z. So the graph is like this. Which means all the elements which are present on this line are stable against radioactive decay. They don't decay. They are quite stable. That's called stability curve. You can see that the stability curve, as you can see, deviates from the straight line towards n, which means as the element becomes bigger, in nature it is found that neutron number is greater than the proton number. This is the observation very clearly seen from the graph. So the question is, why should n be greater than z? Why should the neutron number be greater than z? Or in other words, why should the nature prefer neutron over proton? The answer to this question is, if you have a nucleus, now your nucleons packed in, close packing, imagine there's a close packing. Now there are both protons and neutrons, everything is packed, but protons are positively charged while neutrons are neutral. So what happens is, if we're going to be packing large number of protons, the nucleus is going to be fragmented, or it will not be stable. Because if you're packing so much of protons in such a small space, Coulombian repulsion will ensure that the, the nucleus fragments. Now, to ensure that the nucleus does not fragment, you pack in large number of neutrons because there is a nuclear force between proton and neutron. If this is a proton, there is a neutron, then you have a strong bonding between the two. There is also nuclear force between two neutrons. But the problem with the nuclear forces is they are short range forces. So exist only in the immediate neighborhood. While Coulombian forces are long range forces. So there is a competition between Coulombian forces and nuclear forces. Coulombian forces will take it in a direction where the nucleus is fragmented, while the it's like this. Sorry, if this is the direction of the Coulombian force, then the nuclear force will be in the opposite direction. This is your nuclear force. This is your attractive force. This is your repulsive force. So that's why I'm showing it in opposite. So the Coulombian force tries to fragment or destabilize the nucleus. The atomic force or the nuclear forces will try to stabilize it. So there is a delicate balance inside a nucleus between Coulombian repulsion and attractive nuclear forces. That's how the nucleus remains stable. So how the nucleus in which the balance is not restored, it decays. That is the reason why it decays. For example, here, the elements which are shown here in this region, blue, they are to the left of the stability curve and they come back to this graph by emitting beta minus particle. You know that in a beta minus particle, Z increases. So that Z increases, so it will try to fall towards the right. If it is unstable, it can emit beta minus particle and join the stability curve. The stability curve. The whole objective of every nucleus atom is to join the stability curve. If it is unstable, it does not like to be in a unstable state for a long time, and it would like to emit particles. Now the particles which are emitted are alpha and beta particles. Gamma rays don't alter Z. It only alters the, it is accompanying the beta and the alpha emission. So initially for lighter elements, beta minus is preferred for those elements which are to the left. Now let's see, one second, where is my cursor on? Okay, if you see this region here, this elements join the stability curve by emitting beta plus lighter elements. In some patches of yellow, you can see this yellow patches. If the elements are here, heavier elements, they prefer the alpha route. Alpha and beta plus reduce Z, which means the element will shift towards left, okay, because Z has to decrease. And if the element is to the left of the stability line, it will move towards right by emitting beta minus particle. The beta minus particle increases Z, while beta plus and alpha emission decreases Z. So this is the Segre plot, which gives you an account of how nature behaves and how nature is biased towards large number of neutrons and the reason for that. Let's see some of the statistics here. For lighter nuclei, the number of Z and N are same. You've just seen that the graph is a straight line, but then it deviates. Initially, let me plot this, sorry, let's get this point. Initially, it's a straight line, but then it starts deviating. That's what it said. But for heavier nuclei, this is your N, this is your Z. This is from the Segre plot. N provides balance for the Coulombian repulsion. You see, 60% of stable nuclei have even N and even Z. We will discuss this point later, but it's just putting the stats in front of you. Something about evenness which nucleus seems to prefer. Others have either N or Z as odd. One of them is odd in other cases. There are only five, sorry, there are only five elements which have got odd nuclei. So odd nuclei, odd n, odd z does not represent stability. Even n, odd z or odd n, even z is also not a very good candidate for being stable. The stability is enhanced if you are able to have even n and even z. The other question which also is answered is, why should there be a limit on number of element? You know, the highest element which is found, atomic number, is 118. So why don't you have 120, 140, 150, 170, 200, 2000, things like that? The reason is simple. I said if you have a nucleus, there are neutrons which tries to balance the repulsive proton force. Proton is trying to rip it apart. So what happens is, if you pack large number of protons, because if you increase the atomic number, the neutrons are short range forces. Coulombian forces are long range forces. So despite packing neutrons, there is a limit till which you are able to overcome the Coulombian repulsion. So that's why in nature you don't have elements with atomic numbers more than 118, and most of them are unstable because such large number of protons packed in the nucleus, the Coulombian repulsion is very difficult to be overcome by the short range nuclear forces. That is what it says, that all elements with Z83, understand this, and A greater than 299, they spontaneously transform themselves into diatomers by radioactivity. They are unstable. Any element whose Z is greater than 83 and A greater than 209 is not a stable candidate. The next point which we will see is the nuclear binding energy. These are all very basic concepts which you must have studied in your school, but I would like to reiterate this point because this is going to be throwing a lot of information. We'll be talking a lot about the nuclear binding energy. So if you don't know what is the binding energy, uh, then you will not be able to appreciate the theory. Binding energy, as the very word suggests, there is some energy associated with bond. So here we are talking about nuclear forces which are binding the nucleus. Okay. Now let's take the case of alpha particle. Nuclei are made up of protons and neutrons, but the mass of nucleus is always less than the sum of the individual masses. Now this is very interesting. If alpha particle is made up of two protons and two neutrons, basically there are four nucleons. Individually, if you measure their masses and add them, and if you measure the mass of alpha nucleus, then the mass of alpha nucleus is found to be less than the individual masses. This statistics tells you this. See, alpha particle has got two protons and two neutrons. So 2 multiplied by the mass of proton is the mass of two protons. 2 multiplied by the mass of neutrons is the mass of neutron. So this is the total mass of individual nucleons if you add them, which are the constituents of alpha particle. But if you take the mass of alpha particle as a whole, when they are in a combined state, when they are part of the nucleus, then it is turning out to be less. You can see that 4.00153 is less than 4.03188. And if you take the mass difference, delta m, and multiply it by c square and convert everything into MeV, you have 28.3 MeV is the binding energy of alpha particle. So what does this mean? What do you understand by this? What is the physics of it? It means that if you want to break the alpha nucleus, then you need to supply how much energy? 28.3 MeV. Or in other words, if you have if you have sorry if you have these nucleons far off, let's say these are the four nucleons very far off where their electric fields don't overlap, or not. Then in order to bring them together, if I have to bring them together and fuse them inside a nucleus to form an alpha particle, then I need to supply 28.3 MeV energy. It's opposite. To form a nucleus, this much is the energy needed. To break, if you're able to break the nucleus, then you get this much energy. This is the gain. And obviously, you'll ask me why you have to spend energy in bringing them together, because they are all having uh, nuclear Coulombian forces. They are Coulombian forces. They are a charged particle. Two protons are charged particle. And when they are bringing them together, you will have to work against the repulsive forces. That's why you need to spend energy. But in order to break them, if you are able to break them, what happens is the mass is increasing. So that's why you can see this here. The combined mass is 4.03188. Everything depends on the mass difference. So to fuse them, delta m decreases. Delta m is, it's question of delta m being positive or negative. If delta m decreases, then you have mass increasing, energy increasing. If delta m is positive, then you have to consume energy. So that is what the whole idea is of binding energy. Similarly, the concept of binding energy is also very clear in atom. It's not alone in, if you have a simple hydrogen atom and if you have electron orbiting around it, this is electron, and there is a Coulomb force between electron and nucleus. Now you know that you need to supply energy in order to separate this electron or ionize the hydrogen atom. That energy is 10.2 electron volt. That much is the energy needed in order to remove the electron. And if you're talking about alpha particle, then you can see that the total energy is 28.3. And if you want to find out energy per nucleon in order to remove each nucleon, then you will have to divide it by 4. So around 7 point something MeV would be needed in order to remove each nucleon. Imagine the energy. Here the energy is in MeV, here the energy is in electron volt. The reason is simple, that this is bound only by Coulombian forces, while nucleus, the nuclear forces which are very strong. So you need to supply more energy. Let's come back after understanding the concept of binding energy. Let's come to the most important plot in nuclear physics. I'm making a very emphatic statement, perhaps a graph which has given us so much of information, which I don't think so any other graph has given. Now what we're going to do is we're plotting B by A here for each atom and dividing it by A. Plotting a graph against A. B by A is the total binding energy of each nucleus, and you divide it by the total number of A. For example, in alpha particle, the total binding energy was 28.3 or 4, I don't remember now. Then B by A would be divided by, you have to divide it by 4 number of electrons. So this is your B by A. And against A, you plot the graph, you can see it starts from 0, 50, it goes on up to A, increases, goes up to 230, 240, like that. Now, what is the information this graph says is what is going to be our point of next discussion. Here, you can say that initially B by A is less. There are certain peaks here. Forget about the peak. Let's say it's a smooth graph like that. It reaches a peak somewhere here at iron. More or less there is a plateau, it has reached a plateau, and then there is a fall. Now one thing is very clear, we have seen from previous discussion that B by A is greater than that particular nucleus is stable. The stability of any nucleus will depend on the B by A value, which means it is very easy to remove a nucleon from lighter elements principles. While this mid-range A, the B by A is very large, so it's very difficult to need more energy to remove a nucleon from this mid-range atoms. For heavy atoms, the value of B by A is decreasing. Now, these are also some of the information. The reason why try to answer this: why the B by A value should be less for lighter atoms, why the B by A should be more for mid atoms, and why again it should decrease for heavier atoms. This we will have to understand, and we'll try to give the reason for that. Now, what is the information? This is the information. One information which you've seen is the B by A value is not the same for all atoms. Now, if I fuse two atoms, I am able to move upwards, my B by A value increases. If I am able to break a heavy atom into two parts, then I have a fission fragments which are in the mid range and my B by A increases. So B by A can be increased by two ways. One is fission, and another is fusion. Okay. In fission, you break a heavy nucleus into two parts, not necessarily the same, but the two elements end up being in the mid range where their B by A value is more. So the difference is energy which is released. Okay. In the case of fusion, you have two lighter elements. You fuse them, you move up the ladder. So the B by A increases for the lighter elements as A increases. So what happens is you are able to increase in B by A means you are able to release energy. Okay. Now the question is, that is the reason why lighter elements are fused and heavier elements are undergoing fission. Now you cannot fuse heavier elements. You can't have a fusion. That's why you have fusion of only lighter elements and you have fission of heavier elements. So this graph gave nuclear physicists idea of fission and fusion. This graph told us that if you are somehow able to break heavier elements, you will be able to release energy. Or if you are able to fuse two lighter elements, then by increasing B by A, you are able to increase energy. So this was a very important piece. I think the most important piece of information which this graph has given us, that led to the entire atom bomb, nuclear reactors, hydrogen bomb, and a whole lot of things. It changed the world. Whether changed it for good or bad is a matter of debate. So this is the B by A graph. Now let's try to answer this question which I posed earlier. Why should lighter elements have less B by A, and which means they are less stable, and heavier elements having less B by A? For heavier elements having less B by A, the answer is again large number of protons inside the nucleus. The proton number being more, the Coulombian repulsion is so large that the stability is reduced. Stability is reduced means the chances of decay increases. The chances of decay increases means the B by A value is less. B by A value is a measure of binding. B by A value is less means the binding is less. So that is the reason Coulombian repulsion. For mid-range, this range, there's a good balance between Coulombian repulsion and nuclear forces, and that is why the B by A value of mid-range is are very high. That is the reason why iron is most abundant on Earth. This is the element which is found maximum. The reason is it's very, very stable. Same graph here. This graph is explaining the peaks here. Now I will try to answer this question as to why the lighter nucleus should have less B by A. One calculation I have shown on the slide which will answer this question. Okay. Now I'm taking two numbers. One is 4, another is 8. Imagine you can compare this to be the radius. I have one atom whose nuclear radius is 4, forget about the unit. Another atom whose nucleus has got a radius 8. I just want to compare. Now, okay, number 1. Let me take number 1, calculate the volume. I get this number 268 approximately. Then I calculate the surface area and I get 201. I take the ratio of volume to surface, I get some value 1.33. Similar exercise I do it for 8, I get 2.66. Larger volume to surface ratio means the volume energy is more, means large number of nucleons are in the center. Less number of volume to surface ratio means that more nucleons are on the surface. So if you have a lighter nucleus, this is a medium size, this is a lighter nucleus. If you have a lighter nucleus, then the number of nucleons on the surface is less and on the compared to the total number of nucleons here. The ratio you can see is 0.63. This is the surface. Here on the surface, more you have centered in the center here, large number. Comparing the two. While the lighter nucleus, what happens is you can see the ratio is, the number is almost same, surface to the total nucleons. So you have more number in the surface. Here you can see in this 1, 2, 3, 4, 5, 6. 6 are in the surface and 1 in the center. So the volume, this ratio becomes less. We've seen that also less. So what happens is the binding, this nucleon is properly bounded on all sides. But if you talk about this nucleus on the surface, the binding is only more in the downward direction, while upward direction there is no binding. So any nucleon which is on the surface will be less stable, or it's vulnerable in getting disintegrated from the nucleus. Or if you supply some energy, it's very easy to remove the nucleon from the surface. That's why the binding energy is higher if you are able to pack in more number of nucleons in the center and you have fewer nucleons on the surface. So that is overall going to determine the binding energy of the nucleus. It's basically a question of how many nucleons are on the surface vis-a-vis the total number of nucleons, or compared to the total number of nucleons in the volume or in the center. Center means has got neighbors in all directions. Surface means has got neighbors only in certain directions. There are certain directions where it doesn't have neighbor. So it doesn't have neighbor means obviously the nuclear forces is less. Nuclear forces is less. So obviously what happens is it will not be able to withstand the Coulombian repulsion. Okay. Or if you supply some energy, you can easily remove those. Okay. I'll have to once again explain this. Okay. If I have to remove this nucleon, then if I supply energy, then this nucleon is not very closely bound as the one which is in the center. It will be very difficult to remove this compared to the one at the surface. Okay, let me answer the quiz which I posted earlier. Some of the students had asked me, had some doubt. I will not be able to cover all the quiz, but I'll cover 7 and 8 quiz, and then the other quizzes I'll take it in the next one. Beta emission. There is a problem in understanding energy conservation. There is a problem in understanding momentum conservation. All the two above options. I think you know this is the two options. Neutrino has dash property, has got spin half, spin 1. Half is the fermion. Same spin as electron. In beta decay problem, the missing energy is carried by the daughter. No, it's carried by the neutrino. Which of the statement is true? Electron emission in the beta decay is always accompanied by neutrino. Electron emission, neutrino and antineutrino are the same particle. Positron emission is always accompanied by, actually this was the doubt, this should not be antineutrino, this should be neutrino. So positron emission in a beta decay is always accompanied by a neutrino, right? So my apologies, the mistake. The answer is the question itself, the options. If I have to see the answer is none of them. None of those. I'll have to give a third option. Or I'll have to change the question option. Okay. Beta decay is a two body, it's a three body problem. It's a four body problem, it's a three body problem. Daughter plus electron plus neutron. The three layers here. After the decay, it's a three body problem. It was difficult to have indirect evidence of neutrino because the daughter kinetic energy is too less. You don't see the daughter moving at all, so you don't know whether it's a two body problem or a third body problem. So the third particle's evidence is not possible. If the daughter moved in this direction and if the electron moved in some other direction, you realize that there has to be some particle which will satisfy the momentum triangle. Okay, the detector's Cowan range shows the site of nuclear reactor because it has got abundance of antineutrinos. Correct. Which of the statement is true here? Cowan and rays observed three spikes. No, they observed two spikes. What happened in Cowan rays experiment? Water was replaced. Nuclear reaction was not observed. This is the correct answer. Okay. Which detector was used in Cowan rays experiment? Liquid scintillation counter. You know that this was the instrument. On either side you have scintillation counter 1. This is the chamber and scintillation counter 2. Because you have gamma rays flying, the particle from gamma rays flying up in any direction. So you need detectors which can detect from all directions. That's it. Thank you.